Now, as a theorist, I'm used to trading notion of energy with that of mass. This is what the famous E equals mc squared law tells us. You've probably all seen it. It's the most famous equation in the whole universe, possibly. It tells you that a notion of energy sometimes can be in the form of mass, but also mass sometimes can want to transfer energy. So there's a notion of high energy can correspond to a notion of large mass. But as we've seen, a large mass leads to a large curvature. And so what this tells us is that there are regions in the universe where the curvature is so high that the energy scale associated with it is close to the Planck scale, and we can no longer use Einstein's theory of general relativity to describe what happens in those places. Now, in the solar system, the energy scale associated with the curvature is always very small, even if you get very close to the sun. So we are safe there. It's all fine. We can use Einstein's theory of general relativity to make predictions, compare with the outcome. Whew, that's okay. To reach a curvature related to an energy scale which is close to the Planck scale, we need very large masses confined to very small regions of space. For instance, a black hole. And black holes are not just fragments of our imaginations. Black holes are unavoidable, and they have been observed. On your left, observation from the Keck observatories has been tracking the motion of stars at the center of a galaxy for a period of over 18 years, and you can see that they all seem to orbit an invisible mass at the center of a galaxy, which in fact has all the characteristics of being a black hole. And on the right is zooming towards the very same region at the center of a galaxy, now with the Event Horizon Telescope that measure radial light, so these are fake color, light of a particular frequency coming from behind that very same mass at the center of a galaxy. And we see that light has been bended by that huge mass at the center of a galaxy, and this is completely consistent with how we would expect a black hole to bend light around itself. Now, if you were to find yourself at the center of a galaxy, as you would over the weekend, this is not what you would see. You probably wouldn't see anything. These are fake colors. But what you would experience would probably be quite dramatic. As you get closer and closer to what we call this event horizon of the black hole, the horizon of the black hole, the gravitational attraction will become so large that you could try to run away from it. You wouldn't be as fast as the speed of light, and you wouldn't be able to escape. And once you enter the black hole, enter this horizon, there's no escape whatsoever, even if you were able to travel as fast as the speed of light, no matter how much you're trying to rush yourself out. As you go towards the black hole, you'll be squeezed along the transverse direction and pulled along the radial direction to the point that there'll likely be not much left of you by the time you cross the horizon. The experience may be a tiny little bit painful. And one way or another, by the time you enter the horizon, you'll likely be a little bit dead. However, as you go, I'm sure you'll be very relieved with the knowledge that Einstein's theory of general relativity is completely valid there. This may not be a very safe place for us as human beings, but as a theoretical physicist, that's a perfectly safe territory. We're perfectly happy there. Gravity has been tested at those curvature scales and is perfectly fine. So we can use Einstein's theory of general relativity inside the black hole to predict what will happen, even though we can't really go there. One thing that would happen is that the notion of space and time would switch with one another. And so I can't really discuss about the distance to the center of the black hole. I should really talk about the time scale to the center of the black hole. The distance, if I were to say it like that, is 11 million kilometers. That's about 30 times the distance between the Earth and the Moon. And in time scales, that's about 40 seconds. This is for the black hole at the center of a galaxy. Einstein's theory of general relativity will tell you that as you enter the black hole, you get pulled inexorably towards the center of the black hole, which is located in your future, in time in your future. And as you get pulled towards the center of the black hole, the curvature increases and increases. It increases and increases all the way up to the point where it reaches, the energy associated with it reaches the Planck scale, by which point you can no longer use Einstein's theory of general relativity to trust what happens. So the beauty is that you can trust Einstein's theory of general relativity telling you that it will fail at that point. Precisely what happens there, and even if the notion of space and time makes sense, so even if the very question of what happens there, which precludes the notion of space and time in itself, makes sense, is unknown. All we know is that we need a better description for gravity and for the laws of nature to have a better appreciation of what happens there. Einstein's theory of general relativity has broken down, has failed us before you reach the center of the black hole. So this is our current understanding and description of gravity. We know that Einstein's theory of general relativity is an extremely good description, impeccable description, I would say, for the behavior of gravity on a huge variety of scales. It works well in the solar system, on a galaxy, on a cluster of galaxies, but there are regions, there does exist region in the universe where the curvature is so high that Einstein's theory of general relativity has broken down, and we need a better description to describe what happens in those regions of the universe. Precisely what it is, I don't know. I wish I could share that secret with you, but I don't know. It could be string theory, it could be quantum loop gravity, it could be causal set, it could be something yet entirely, I don't know. One of the challenges that we have at the moment is understanding how, with an underlying framework which we don't know about, how can we make predictions for what we should observe today? This is very challenging, but this is some of the work that my collaborators and I, and a big part of the scientific community, are trying to do at the moment. However, what I'm even more interested in is to understand what happens at the other side of the spectrum. That's another secret of gravity I'd like to share with you today. So what I'd like to understand is, if gravity fails us on very high curvature scale, could it be that gravity also fails us on, or I should say Einstein's theory of general relativity also fails us on very small curvature scale? So to understand how to look at gravity in regions of the universe where the curvature is extremely small, what we should do is zoom to the largest possible scales in the universe. So we can zoom out of the solar system, zoom out of the galaxy, zoom out of a local cluster of galaxies, over distances that span over billions of kilometers. It would take us millions of light, it would take us millions of years to get there if we were traveling at the speed of light. What we see on those distances is that clusters of galaxies are distributed along filaments of dark matter, which are represented here in blue, but these are just fake colors. We can't see dark matter because light doesn't interact with dark matter, so we wouldn't see that. This is just an animation. So if we were to look at this picture, we may be under the impression that most of the energy present in the universe is localized along this filament of dark matter and clusters of galaxies. Something else remarkable when we look at the universe on those scales is that we realize that the further away we look at an object, the faster it seems to be moving away from us. And that doesn't tell us that there's something very specific about us, that we're very smelly and everybody wants to run away from us. What it tells us is that the very structure of space is expanding, is being stretched apart. The universe is expanding. It is the very structure of space which is expanding. The universe is not expanding into anything. The universe itself is expanding in itself. Now, there's one thing we know about gravity, which is we're all connected to gravity, and it is a gravitational attraction, which means that if it's true that most of the energy present in the universe is present through these masses around dark matter and clusters of galaxies, we would expect them to exert a gravitational attraction on each other, and slow this expansion of the universe down. Maybe there could come a point where the expansion of the universe has been slowed down so much that it will stop, and it will stop expanding, it will start contracting instead. This is possibly what we would have expected. At the very least, we would have expected the expansion to slow down. But when we look at the universe on even bigger scales, what we see is exactly the opposite. The expansion of the universe is going faster and faster. The universe is expanding at an accelerated speed. This acceleration of the expansion of the universe is one of the greatest puzzles of modern physics, and is contrary to what we would have expected if indeed most of the energy present in the universe was confined in the clusters of galaxies and filament of dark matter. So to see if that's really the case, what we can do is zoom into a completely empty region of the universe, far, far away from any clusters of galaxies, far away from any source of life, in the middle of what we call a cosmic void. Imagine how lonely you would be there. There'd be no one to talk to, no planet to land on. You wouldn't even have a black hole to dive into to get yourself entertained for a little bit. And yet you wouldn't be truly alone. Because even in the best vacuum, you're still filled with all of the quantum fluctuations from all of the particles that we know of from this vacuum bath, including that of the Higgs. And as we said, this should have an effect on gravity. But the effect that this vacuum bath has on gravity is very different as compared to the effect that you and me and planets and stars have on gravity. When we're thinking about the way a planet curves the structure of space-time around itself, this is something very localized. It's just around itself, it curves this fabric of space-time. But when we're talking about this vacuum bath, it's not something which is just localized at some time or at some position in the universe. It actually fills the whole space in the universe and has done so since the very beginning of time. For billions of years it's done so, and it does that through the whole volume of the universe completely uniformly. So what it does is not curve space-time just locally at one point. What it does is push the boundaries of space-time. There's not such a thing as boundaries of space-time. It pushes space-time as much as it can in every direction. This vacuum bath actually leads to an accelerated expansion of the universe, which is actually exactly what we are observing. When Einstein came up with the theory of general relativity, he didn't know that the universe expansion was accelerating. Actually, he didn't even know that the universe was expanding. Also, he didn't know that there was such a thing as a fundamental particle leading to a vacuum bath, including that of the Higgs. But now that we know all of this, we can put those ingredients together.